Welcome everyone. So this is a great pleasure for me to introduce this Rothschild lecture. For those of you who don't know, each of the 6-month programs that the INI runs, the organisers get to choose a Rothschild professor who is a very distinguished academic who is there to kind of inspire the whole program, and we could think of no one better than Peter Bühlmann to do that. Peter is a very well-known figure in the field from ETH Zürich. I won't want to list his many honours and achievements, but let me hand over to Peter, who's going to speak today about causality, invariance and robustness.
Okay. So, thank you very much, Richard. I should also say it's a very special honor for me to give today this special lecture, and I should also say I always enjoy coming to Cambridge. This is a great place, and I see always many friends here, and I'm always newly stimulated about new research when I come here. So I'd like to acknowledge my main collaborators in this research. This is Jonas Peters, Nikolai Mainshausen, and Dominik Rothenhäusler. And in my talk there appears the word of causality, and I start very way back. Happy is she who is able to know the causes of things. And it is true that, of course, already in ancient times people have debated on causality because it's such a fundamental question. Today I want to show you a bit that we can discuss this question as a prediction problem, namely predicting the effect of an outside intervention, which maybe makes this whole problem a bit more pragmatic. But first I want to start with a warm-up exercise. Well, it's maybe well known, but maybe you should be reminded that correlation is not the same as causation. And here's a real data example. So you see on the x-axis you see chocolate consumption in kilogram per year per capita, and on the y-axis you see the number of Nobel laureates relative to the population per 10 million population. And UK people, they eat quite a lot of chocolate and they receive quite many Nobel prizes. This is real data. The correlation is 79.1%. It's highly significant. Okay, this is a fact. You cannot argue against it. The only issue is about interpretation here. And maybe you have your own interpretation, or you can read also what people are writing. Eating chocolate produces Nobel Prize winners, says the study. Okay, sounds good. And here's another one. Geniuses are more likely to eat lots of chocolate. Maybe sounds good too. And if you think about to formalize this a bit, there are basically maybe 3 scenarios which we can look at. And we can actually use a bit math type formalization. So we look at graphs, and the 2 variables are x and y. X is the chocolate consumption, y is the chance to obtain the Nobel Prize. And one scenario would be indeed chocolate produces the Nobel Prize, so x would point to y. Or this is the other one, geniuses eat more chocolate, so y would point to x. Or there could be a hidden confounder, something which you have not observed, but something like wealth of the country, and maybe this unobserved confounder actually creates this spurious correlation, this dependence between x and y. Okay, maybe you have your own theories, what you like here, but clearly an experiment would be most helpful. And actually you should do a randomized control trial, a randomized experiment. This is considered to be the gold standard. And what it means is you force some people to eat lots and lots of chocolate. And that, I think, is a very great idea. And let's do this, actually. So I do this randomized experiment. I do this certainly randomly. So Siggy gets one, you don't get anyone. Sorry, Lisa. You get some. And we randomize this a bit. Okay. And I think they should have some. And here a bit more. Okay. So we randomize. And some of you have gotten the chocolate, and the ones who got the chocolate, they will be forced to eat every day lots of chocolate. And the other ones who didn't get the chocolate, unfortunately, he will be banned from eating chocolate over many, many years. We wait 20 years, very long, and then we compare, right? And of course, you have to promise me, you give me the information when you got the Nobel Prize, and I make a checkbox. Okay, so that's the randomized control trial. And so the important part here is actually the randomization. So what is actually the randomization doing in very kind of folklore terms?
May I just make a point here? The randomization itself may be causative, in that some of these poor people didn't get any chocolate. They are now completely fed up with whatever they're doing.
Well,
They're going to go out and get drunk.
You can have mine, Ted. I don't mind.
so the one who didn't get a chocolate, they will get one from me at the end of the story. Okay. So here is the problem with the hidden confounder. And so it could be wealth, it could be also cliques of people, right? And here is chocolate consumption, here's the Nobel Prize. And if you would do a systematic intervention, if I would give all these people here on the left some chocolate, I don't break the clique structure. Maybe the people are sitting together in cliques, they help each other to get the Nobel Prize, and so that would not be a good idea. In order to break this dependence here, I need to do a randomization, a randomized assignment, and then you break the dependence to this hidden, unobserved confounder, and through that you conclude as follows. If now you see an effect of x to y, because you broke that dependence, it must be that x causes y. Okay, this is a great machinery. Fisher already mentioned that in 1918. This is at least my knowledge of the history, but he did not formalize it. And then Neyman in 1923 was first to give a mathematical framework in a potential outcome model, and then soon after again Fisher 1925 said yes, actually randomize, and he was a very strong kind of supporter of randomization, and then very quickly RCT's randomized control trials gained acceptance and became the gold standard to do these kind of causal inference. If you think about historically, RCTs are extremely recent in the long history of science. So, for example, Newton or Gauss, they did not know randomized experiments. They knew, of course, about experiments, but not about randomized experiments. And so RCTs is really an invention of the 20th century. Okay, so there are, of course, problems with randomized controlled trials. We've heard one problem here, there are a couple others. Randomization can be unethical. Yes, indeed, you didn't get a chocolate. This is a bit unethical. There can be a very long time horizon. There's an issue with reliability of participants. This is the non-compliance problem. There are high costs, and so on and so forth. And so the question is, and I want to discuss this a bit today, what can we say without having an RCT? And to make the point clear, it will never be fully confirmatory, what I will say now or next. And there's the famous case of Fisher with smoking and lung cancer. Many of you know that story. You cannot make a confirmatory conclusion if you don't have a randomized control trial. Okay, so what can we say without RCTs? And the point here, which I want to discuss a bit, we go much more into the direction of prediction. And if you think about it, causality is about giving a quantitative answer to a what if I do question or a what if I perturb question. But the point is I have no data on this perturbation. And so it is really about predicting the outcome of an unobserved manipulation. So here are examples. This is actually a question which appears very many times in modern applications. The first example is a bit more to the area where I'm personally exposed to, so say in genomics. You could ask the question, what would be the effect of knocking down, manipulating a single gene? What would be that effect on a response variable of interest? And the response variable of interest here was the growth rate of a plant. It was actually the Arabidopsis plant. So you want to predict this gene knockout actually without having data on that. Or in e-commerce is also very popular nowadays, and actually Google and these companies, they do that. The question is, what would be the effect of showing person, call him XYZ, an advertisement on social media, but there is no data on such an advertisement campaign for this person XYZ or for similar persons like XYZ. So you want to predict what would happen if I show Lisa this advertisement, but I have no data on it. Okay, so here's the potential outcome model which formalizes this a bit. So here are two famous people, Jerzy Neyman, who kind of laid a foundation for that, and Don Rubin, who made many contributions in this potential outcome model world. And the question in a way is, again, what I said before, the potential outcome, we ask the question, what would have happened if we would have assigned a certain treatment to a certain person? And I'm using the subjunctive here because I have no data on it. It's kind of a potential outcome. And so here is a bit the picture, what we are trying to do. This is synthetic data, and then I come to real data. So suppose you measure variables x and y. Okay, like chocolate and Nobel Prizes, this is something different. You see a correlation, and now we make a potential outcome. We say, okay, what would happen if x would be -8? What would be the prediction? Well, if you believe in regression, you would say, okay, I make the prediction here. That sounds good, right? But in fact, what's underlying this principle is x causes y, right? If I manipulate x, it changes y, and according to the kind of effect which we have learned from the data. So here's the next picture. It could also be I manipulate x, but y causes x, then nothing happens, and then the resulting value of y is kind of the mean of your observed data. And so what we're trying to do in a way is to make a prediction based on the black bullets, should it be this or that. Okay. And this is actually a real problem. So this is gene expressions. This is activities of gene. I'm coming back to this problem. Here we measure the activity of genes. This is an X gene, this is a Y gene, and this is what we have observed, the blue stuff. If you see the blue stuff, you see some sort of a regression. Then you do a manipulation on the X gene, and actually what happened is it had a huge effect on the Y gene, and the value was down here. Here's another problem. I see two genes, two gene activities, an X gene, a Y gene. I see something in the data, that's the blue stuff. I do a manipulation, and actually the value is there was no effect. And this is of course the same problem from before. I need to distinguish how can I actually predict whether it should be down here or up there. It's a challenge, so how can we predict such a potential outcome? And what I try to explain a bit today is we exploit invariance. And so here's a picture. I kind of try to link that a bit to some sort of big, large-scale data, which is heterogeneous. I think of the setting that I have a lot of data, and this data is heterogeneous because we believe, or we see actually, that a lot of large data has subpopulations, heterogeneity structure, and an IID assumption or a stationarity assumption is not really appropriate. Okay, so it's quite a common setting, and here I try to make that a bit more precise with very simple examples. So we think that we have data from different known, call it environments, call it experimental conditions, or call it perturbations, or subpopulations, and this is always denoted with a little e. E denotes an experimental condition, an environment. And this E actually lives in the space script D, so script D is the space of subpopulations which I observe in my data set. And I'm thinking of a regression classification type problem, so I have covariance X, I have response Y, and they have a distribution F, and all these things depend on little e in the subpopulation in the environment. So here are very simple examples. The first one is I have data from 10 different countries. I have 10 different subpopulations, and I would encode these subpopulations with e equals 1, 2, up to 10. Okay, very simple to do. We can think of data from different economical scenarios, and now the different environmental conditions are typically blocks of consecutive time points. And I have periods long time ago, this is one environment, and the next period, and so on. So blocks of consecutive time points are my environments which I have observed in the data. So script D is really the environments, the subpopulations which I observe in the data. Now, we're looking at something much larger. We're looking at a space script F, which is a much larger space than what I observe. And these are many possible, but mostly non-observed environments or perturbations in this much larger space script F. Data examples from before, script F could be the 10 countries, that's how I have observed that, and maybe all other countries in the world which I have not observed in the data. Or the economical scenarios, it could be the environments which I have seen until today, and all the future scenarios which I have not seen in the data. That would be my script F. And the problem is a prediction problem, predict y given x, such that the prediction, call it works well, is robust for all these environments E in this much larger space script F, but now based on data only from this much smaller script D. I want to make a prediction which works well in an environment which I have never seen in the data. So this is a very fundamental problem. Here it again, predict y given x such that the prediction is robust for scenarios which I've never seen in the data. And for example, with linear models, you can kind of mathematize this a bit. So you could ask, for example, the question, give me the regression parameter which optimizes a worst case risk over all scenarios in this script F, which I have not in the data. Well, this is kind of a... Yeah.
It is one thing to sort of set up a linear model as if somehow there is a relationship between future environments and the present environment. But what sort of assumption do you need to make in order that there shall be some relation between the present and the future?
Yeah, I'll try to explain this a bit, maybe. So we need to make assumptions on what these perturbations are, right? We need to have a model on the perturbation. We need a model, and I try to explain that model a bit. And there can be many questions about the model. The model should be good, should be justifiable somehow, and should lead to, let's call it, reasonable empirical results. Okay. So, just to continue a bit with this way of thinking, one may call this causality. Because, as I tried to point out already, we want to make a prediction of an environment, of a perturbation which we have not seen in the data. And if I look at this optimization problem, I try to optimize a worst case risk. It comes a bit to that. If I look at perturbations, at subpopulations, if my script F are all perturbations which do not act directly on Y, I'll explain it a bit more. But if this is my model for F, then the optimizer here is what people call the causal parameter. Okay? So we think this is interesting because the causal parameter optimizes a worst case risk. Okay. So let's try to come back to that in a moment. But of course other people call this robustness. They say, okay, I want to be worst case optimal in a class F of perturbations. This is nothing new. And there are relations, of course, to say robust statistics, but it's a bit different in the way that, so in robust statistics, the script F would be perturbation, say, in the neighborhood of a Gaussian. And here the script F is perturbations which happen in future data, which I have never seen in my data set. So there's a bit of difference here. There are also connections to robust optimization, where they say, okay, the parameters are uncertain, they are perturbed, and then you do a robust optimization version. Maybe if I have time, I'm coming back to that a bit later. Okay. So I'll come into your question, but before I want to show a bit what is kind of the guiding principle, how we try to exploit heterogeneity to get to something which is robust, or get to something which actually gives you the causal solution. And we call this actually invariant causal prediction, and I'm trying to give you a bit a vague overview of what that is. And the main message actually will be that the causal structure remains the same for different subpopulations. I'll make that more precise. The non-causal structure, it can change over subpopulations, over perturbations. And so if this is true, then you simply have to look for stability over different perturbations. Okay? If this is true, there's kind of an easy solution to that. I mean, in a nutshell, we just have to look for stability of structures across many perturbations. And a key assumption to make that work is what we call an invariance assumption. And so what is that? So the invariance assumption with respect to this space script D, this is the space of observed environments of observed perturbations. It could be also for other spaces. The assumption reads as follows. I have D covariates, I have D-dimensional covariates X, and the assumption reads there exists a subset of covariates, call it S star, such that, and now comes the point, the conditional distribution, if you condition on S star, this conditional distribution remains invariant across all perturbations in this script D. So if somebody gives you this S star which satisfies this condition, you know the conditional distribution remains the same. So what does that mean, say, in a linear model setting, which is easier than to do the statistics? It would mean there exists a regression parameter vector, call it gamma star. It has support set S star, such that for all perturbations, for all environments, I can write YE is XE, same regression parameter, plus error term. The error is uncorrelated of S star with the same distribution of the residual term. Okay, this is just a translation of that. XE itself can shift a lot, can be perturbed a lot, so the covariates could go all over the place. You can say, okay, this is interesting in its own right? Somebody gives you a set S star, you condition that, if you do it empirically, and then you would realize, aha, I always get this more or less the same regression parameter and more or less the same residual term. So from a practical point of view, this is kind of interesting, and this is also what people, I think, in science or in many science applications find interesting. You find some sort of a structure which remains invariant over many perturbations. Okay, now you can ask for the invariance assumption with respect to this much larger space script F, which is not seen in the data. And it's the same condition. I just assume there exists a set S star of covariables such that the conditional distribution remains invariant over all environment in this much larger space script F. And now gamma star and S star are even more interesting, right? Because it says something about unseen new environments, something which you have not seen in the data. Of course, you make an assumption, and we now want to talk a bit when does this assumption hold. And there's a link to causality here. Of course, causality is a very huge topic, and I give you a very, very toyish definition of causality, which I can give in 1 or 2 minutes. So what is actually a causal variable for y? If we mathematize this, we can go the following route. We can think of an underlying causal influence diagram. It's a DAG, so if an arrow points from x11 to x10, it would mean x11 has a causal effect on x10. And you put a model on that graph, and the model is a structural equation model. And you say, okay, my response y is just a function. It doesn't need to be linear. It's a function of the parental variables, comma error term. And also all these covariates xj are functions of the parental variable, comma error term, and the error terms are assumed to be independent for the moment. So there are no hidden confounders. I'm coming to that later. And so what are the causal variables for y? The simple definition is that direct causal variables for y are the parental variables for y. Okay? Now, the problem is, under what model, for the perturbations, can we have, say, an interesting description of these invariant sets? So I have this invariance assumption. I want to see which set satisfies, and the question is now, under what model for my perturbations do I get an interesting description? And loosely speaking, we assume 2 conditions. The third one is not really a condition. The first condition is, and this is a graphical description, I have my environments, My subpopulations, they come from a variable E. And the assumption in such a structural equation model would mean the environments have no direct effect on Y. That's maybe a big assumption, but let's make that assumption. And the other big assumption is the environments do not depend, the relation between X and Y does not depend on E. So E does not change the relation between X and Y. If everything changes, it's kind of an impossible problem. And of course, the environment, they can change the X a lot. And of course, usually we don't do this, we just show this, right? We just delete the arrow. Okay? So it's very easy, it's a two-line proof, and I spare you that. The following result is true. I assume a structural equation model for Y and X as before, then I can talk what a causal variable is. I have a model for my perturbations, and that was a bit a question here. My model for the perturbation is this. The perturbations do not act directly on Y, and they do not change the relation between X and Y. And of course, the perturbations can have arbitrary effects on X. And then the statement is the causal variables actually satisfy the invariance assumption. So under these assumptions, the causal variables satisfy invariance, so if you condition on them, the conditional distribution remains invariant. Okay? So this is kind of a link. It's a model for my perturbations. It's a structural equation model for my observed variables, and then the statement says the causal variables satisfy the invariance assumption. Maybe other sets of variables satisfy it as well, but the causal is an interesting candidate. So causal variables lead to invariance under arbitrarily strong perturbations from F, so there can be super strong perturbation on the X's, but not directly on Y. So here's again the results. And now you can kind of see that it is plausible why the causal solution optimizes this problem. Let's look at the worst case risk over all scenarios E in this script F, and F actually satisfies these conditions. It does not directly influence Y and doesn't change the mechanism between X and Y. And if the perturbation can be arbitrarily strong, you should look for something which gives you an invariance, and the causal variables give you invariance, and actually the solution of this problem is the causal parameter. So in a linear structural equation model, that is the solution, loosely speaking, because if you condition on the causal variables, the conditional distribution remains the same, and that's in a way somehow the worst case. Okay, so again, this is the result, and this is the description, and this is a bit a question. If we look at the model for F, and the model has these two assumptions here, then indeed the causal parameter optimizes this worst case risk. Okay. If the perturbations in F are different, and I'll talk a bit about that, so we can have different models, then we have a different solution. It will not be the causal solution. Okay, so here is a real-world example. I pointed to that already a bit. Let's see whether these assumptions make sense. That's a bit the point of this slide. So this is my plant, my Arabidopsis plant. Y is the growth rate of the plant. That's my response variable. I have very high dimensional covariates of gene expressions. And what has been the data which we actually had? So this was a collaboration. And so we had observational data. Let's encode this with E equals 0. And then people already did some single gene perturbations. Maybe they knocked out gene 7, then they knocked out gene 10, and they did M gene perturbations, maybe 20. So they did 20 single gene perturbations, and I can encode these perturbations with my labels 1, 2, up to 20. Now let's think about these conditions. So this perturbation acts in an arbitrary way on the expression of the gene I'm knocking out. If I'm knocking out gene 7, that perturbation has a lot of effect on gene 7, and maybe also other genes. That's fine. But presumably it's plausible to say this gene perturbation does not directly act on the growth rate of the plant. If it changes the growth rate, it changes it through the genes. It's not the perturbation on the gene which directly changes the growth rate. And so it's plausible to say, yes, it's true, or it's plausible that it does not directly influence the growth rate, the perturbation. The second assumption, I have no clue. How the heck would we know whether a perturbation would change the whole system or not? This is a very hard problem, and we need to make some sort of first order conditions, and this is a first order condition that we say it doesn't change it. And of course it changes the x's a lot, and that's fine. So this is kind of justifying to a certain extent the assumptions which we make. So we've seen a bit this interplay between causality and invariance, and we just argued that the causal variables, they lead to invariance. And this is known since a long time. Havelmo in 1943 kind of implicitly had this in his paper. This is a picture of Trygve Havelmo. He was a Norwegian economist who later got the Nobel Prize. So he was very, very early, and actually people in economics realized quite early this issue of if you condition on the causal variables, you get invariance. So there are other people, one of them is in the audience, who worked with that framework as well. More novel is maybe the reverse relation. Can we actually go the other way around? Can we say, if I see invariance, can I get something about the causal structure, or can I do some sort of robust predictive stability? And let's just briefly talk a bit about this. So I want to go, can I say something if I see invariance, can I go to the causal structure? And the idea of that novel direction, and why is it novel? Because maybe we just have more data now which allows us to do that. The idea is, okay, I search for invariances in the data. I can do that, right? I see heterogeneous data, I condition on variables, and I check whether it remains constant or stable or not. I search for invariances in the data, and then there's a bit an issue here how we get to the causal structure. But searching for invariances in the data is not so difficult. Say in a linear model, I just run statistical tests. I check whether I have the same regression parameter and the same residual variance or the same residual term. This is an old problem. You can go back to, say, Joe, and he tells you how to do that. So this is one thing. I can search for invariances in the data. That's not so hard. And then in addition, you need to address subtle identifiability issues, and I'm not going into details about that here. But the underlying problem is it's not only the causal variables which satisfy invariance. Other variables, other sets of variables satisfy invariance too, and we have to deal with this identifiability issue. At the end of the day, you get an algorithm, a method, call it S hat. It depends on what kind of environments you have seen in the data on this script D, and this is the set of estimated causal variables. And it has a certain property that you don't get false positive causal selection. So if you see something in S hat D, it must be a causal variable with controllable probability. I'm not saying anything on power, so S hat D could be the empty set. Then I would have bad luck. I run this, I see the empty set, I don't see anything. Okay. The good thing is, if you believe, of course, all these assumptions, if S hat D contains something, then it must be a causal variable. We call this ICP because it kind of searches for invariances, and it's kind of invariant causal prediction. So let's see how this works on a real data problem. So this is single gene deletion experiment in yeast. So the problem is as follows. We measure all the genes in the genome of yeast. There are a bit of more than 6,000 genes. We measure their expression values. And the response of interest, let's put it in this YX framework, the response of interest Y is, say, the expression of the first gene, and the covariates are the expression of all other genes. Then I can do that again. The response of interest Y is the expression of the second gene, and the covariates are the expression of all other genes, and so on and so forth. I can do this 6,170 times, right? And at the end of the day, I want to do this potential outcome prediction. I want to predict the effects of unseen new single gene deletions. I want to predict the effect of a new gene manipulation, which I've never seen in the data. So the data is as follows. It's actually quite good data. So they measure genome-wide mRNA expressions. They have 160 observational measurements. This is a lot. So in this lab, this is actually in the Netherlands. This is the Holstege lab in the Netherlands. They measured 160 times the unmanipulated yeast. So this is a lot of measurements. And then they already have kind of manipulated 1,479 genes. So they knocked out 1,479 genes. No replicates, unfortunately. They just knocked it out and see what happens. Okay, how you put that into the method? I have environments. My environment 1 is observational data, and I pool everything environment 2 into one environment because I need some sort of statistical power. If I have 1,480 environments with the observational one, some of them would just have a single data point and they cannot do any statistics. This is very crude, maybe it's not optimal, but let's see what's happening. You do a training test data splitting, so you train your method on all the observational data and 2/3 of the interventional data, and you hold out 1/3. 1/3 of gene knockout experiments is set aside, and you want to predict them, and then you check. And you treat this for the 3 blocks. You do some sort of multiplicity adjustment because you run this 6,170 times. Okay, what are the results? 8 genes are found to be significant at a 0.05 level. 8 genes are causal for another gene. You say, okay, that sounds great, right? Well, maybe it's not so great if you look at it from this way. This is very, very few findings. If you think about this as a graph, these 6,170 genes are the nodes in the graph, and in this entire graph, I say 8 directed connections. That's almost nothing, right? But the point would be, if these 8 are at least the true ones, it may be not so bad. Well, okay, we use a very stringent multiple testing correction. I'm not sure whether that is the reason. We just find 8. The point is, I have put 1/3 aside, and I can check and validate. So how do you validate? This was the picture from before. This is how it really looks like. So here is a strong intervention effect. Here was a gene manipulation. Maybe you have put it aside, and it actually had a huge effect on the Y gene. And that would be a strong intervention effect. And here would be a gene manipulation. It had no effect, so it would be a 0, right, in your holdout data. And the question is, are these 8 genes now, these 8 significant causal variables, are these strong intervention effects? And the answer is 6 out of the 8 are validated as strong effects. Okay? So you claim 8 to be significant, and 6 of them are strongly validated. And you can look at this as a sort of ROC type plot. Here you would kind of rank with any algorithm or method. This is my top prediction. This is the gene which gives me most likely a causal effect, and so on. So here is the first, the second. So it is kind of how you rank your predictions. And here are the true positives. They were strong intervention effects. And so this invariant causal prediction is actually the red line here. And the surprising part in some sense is, okay, let's look at the first prediction. True. Second true, 3 true, 4 true, 5. The first 5 predictions, they're all strong intervention effects. They all found it. The 6th is nothing, the 7th is true, the 8th is nothing, the 9th is true, and then you're done. Then it levels off. And the orange one is a version of that which includes hidden variables. What's maybe hard to see in the back, there is kind of a gray shaded area here. This is random guessing, and these are other methods. They do about as good as random guessing. So it levels off. Well, it's a very, very hard problem. It's a very ambitious problem. We find somehow the top 5 predictions, they're true, that's great, but we don't find more, so I don't want to exaggerate more than that. It's a hard problem. It's this problem. Tell me whether it's this or that. And this is what we're trying to do. And the top 5 were correct. Okay. So in the remaining time, I want to move a bit away from causality because it is very ambitious. It may be sometimes too ambitious. We don't know whether these conditions hold. And also, if you think about it, the perturbations in what I call the future data in my script F might not be so strong than in a gene knockout experiment. I mean, these perturbations were huge, right? You bring out, with a manipulation of the gene, you bring out the activity into a completely different range. And so more pragmatic is just the viewpoint, just construct the best prediction in heterogeneous settings, and that actually adds some sort of a novel robustness viewpoint. And we're kind of looking at this problem with a certain approach. There might be other approaches, and we call this approach anchor regression. I'll explain why anchor, and something which we call causal regularization. And so this works as follows. So now I switch notation. I have before the environments, my different subpopulations, and they are now outcomes of a variable which I call A, and this variable is an anchor. Okay? And so the picture is, okay, I have my different environments coming from this anchor, and it has an effect on X, it has no direct effect on Y, and you have a structural equation model. Then people say, okay, I mean, this is not a very good model, and of course people looked at this model. They said, okay, they could be hidden confounders, and well, remember the chocolate example, they might be hidden confounders. So we better include hidden confounders in our model, and that model is well known. This is the instrumental variable regression model. So economists, they kind of came up with this first, they call this an instrument. We call it an anchor, you'll see in a moment why. They call it an instrument. The instrument has an effect on X, has no effect on the hidden confounder. How the heck do you know that? And has no effect on Y. Okay. So this also appears in other areas, not only in economics. People, say in genetics, they use Mendelian randomization, and this is exactly the same problem here. They actually have this kind of A, the instrument is genetic information, X could be gene expressions, and Y could be your phenotype, your response. So it's very, very popular in genetics. So our point is a bit, why do you know that the instrument is not pointing to this H, this unobserved confounder? You even don't know what it is, right? And you kind of bet that your instrument will never point to this unobserved confounder. And we say, okay, we allow that A actually could point to H. A could also point to Y. I excluded that before. And the only assumption is that A is a source node. This is my only assumption. In economics, people would say this is an exogenous variable. A is a source node in a graph, and this is why we call it an anchor. That's the only assumption. You could have feedback loops, and here is a linear structural equation model of that model where everything is kind of possible except that A is an anchor, and so you have this additional exogenous term.
Excuse me, why do you distinguish between anchor on the one hand and causal variable on the other?
Yeah. So the question is whether the anchor could be an X, or is that the question? Or?
I guess I've missed this distinction. In a network, the arrow goes that way, so the anchor is causal on X.
Yeah, that could be possible. So that no, that's not. So the anchor must be a source node, so it must go away from A. Is that the question?
Just trying to connect it with your previous network in which you distinguished causal variables.
Yeah.
One variable causes another.
So I'm interested in kind of the causal relations between X and Y. And so I have here a bidirected arrow because it could be a model actually with feedback loops. It's a bit more general than before. And so there is unobserved confounding, which could complicate the problem. And this anchor is really kind of my different environments. Say over time, I see different environments. And then that would mean, okay, the time just influences these variables, but the variables themselves, they don't influence the time.
A is something not influenced by anything else in your diagram. Maybe I'm confused that this A, I'm thinking of it as a variable, but you'll think of it as a whole set of something, aren't you?
Yeah, it could be, it's a multivariate, yeah.
Right.
I mean, all these things, say this is a one variable, this is one dimensional, but this is d-dimensional, this is q-dimensional, it could be, yeah, otherwise it's a bit difficult. Okay, I said that before. The anchor model is a generalization of instrumental variable regression because we allow for the edges also to H and to Y. Okay, so I excluded that before, right? I said before the environments are not allowed to directly act on Y, and now they are. So the environments, the anchor can point to Y, it can also point to the hidden confounder, and then there's a problem. There is a fundamental identifiability problem, and you can never get the causal solution. But you can get something still which is not too bad in our view. So you cannot identify the causal mechanism between X and Y if you have an anchor or kind of an instrument which would also influence H over Y. Okay, so this is what we mean by causal regularization. We don't give up with the problem. You can say, okay, the problem is not solvable. It's true. For causality, it's an unsolvable problem. But I want to show you that we can offer something. And the motivation is, in a way, again, invariance. I told you before that invariance is very, very important and connected with causality. And here we just have a result, actually, which is non-trivial to show. You can show that the residuals are not entirely invariant, but so-called shift invariant. And I'll define it, what it means. They are shift invariant if and only if the anchor is uncorrelated with the residuals. Just believe me that for the moment, but if this is true, if the residuals are somehow a different form of invariant, if they satisfy this, then this is only and if and only true if A is uncorrelated with the residuals, then we have some sort of a strategy how we want to do estimation. And the estimation could be something like, I call it beta tilde. You minimize residual sum of squares in a linear model, and you encourage orthogonality with A, right? So you add this additional term here, this kind of inner product, and measures orthogonality. And if psi is large, you kind of encourage more orthogonality with respect to A. So this is almost what we do. We do it a bit differently, but it's the same idea. And I think this one is maybe a bit simpler to explain. So what we do, and this is our anchor regression estimator, we look at minimizing the anti-projection on the row space, on the column space of A, length squared, plus a regularization term times the projection of the residual squared on A. And if gamma is 1, this is an easy case, this is ordinary least squares. You can always decompose least squares in the projection on A and the anti-projection. Okay. If gamma is large, you enforce orthogonality with respect to A. And so we have any gamma, which we can choose here, and we call this causal regularization. Well, if you have a high-dimensional problem, you can add a sparsity penalty, it can all be done. This is a convex problem, you can solve that. Well, what does it mean? There's a fundamental identifiability problem. You will not get the causal parameter. But causal regularization, as I just showed you on the previous slide, is solved for optimizing a worst-case risk for a certain class of perturbations. And now we need again to talk about what is the model for the perturbation. And the perturbation model is the shift perturbation. So in this anchor regression model, I have observed heterogeneity through my anchor variable. This is this heterogeneous variable. I have my structural equation model. I have this additional heterogeneity which I observe in the data. What is the shift perturbation in new scenarios? It's the same structure. It's kind of dynamically written, and instead of this observed heterogeneity, you have a shift. V is just a shift. It could be random, could be deterministic. The shift is actually in the span of M, and we can measure the size of the shift. If gamma is large, it's a large shift. If gamma is small, it's a small shift. And this is the technical definition. But gamma just measures the length, the size of the shift. Okay? So this is my perturbation model. This is for my script F. And so here's a kind of a fundamental duality which links these things. And this is actually for the population version. So if PA is the population projection onto A, okay? So this is just a conditional expectation. The result is, for any regression parameter, you look at the worst case risk, okay, over shifts in this class C gamma, and gamma measures the strength of your shift. So this is a worst case risk over shift perturbations, and that is exactly equal to the criterion function to the objective function of my anchor regression estimator. So what is it? It's the anti-projection on A of the residual squared plus the regularization term gamma times the projection of the residual squared. And the gamma is the same. So if I penalize by gamma, it has a particular meaning how strong the shift is. Okay? So worst case shifts in dimensions correspond exactly to this regularization, and this is really kind of fundamental and interesting. So of course, if you have this holds for any b. We can think of this as a worst case test error. This is my worst case test error, right? It says this is the criterion on the training sample. Of course, what you do is you take the argmin, because it holds for any b, I can also optimize it. And that is somehow the justification that this anchor regression estimator, this is a finite sample version, indeed protects against worst case shift interventions. This can be made rigorous in the high dimensional sparse setting, but the point is this regularization corresponds to worst case risk. So what have we done to address the ill-posedness here? So if the anchor points to H, it points to Y, it has a direct effect on Y. I excluded that before, now I allow it. What do we do? People say it's ill-posed, and we do something. Well, if you just want to have predictive stability, you just want to predict. You want maybe to predict against worst case scenarios, maybe in economics, then you choose a gamma. You choose your robustness degree. Maybe between 2 to 5, because this gamma has a meaning. If I choose it as 2, it roughly means it's an amplification of the observed heterogeneity by the factor 2. If I choose gamma 5, it's a 5 times amplification of the heterogeneity which I see in the data. Okay, so we can do that. I mean, nobody knows in a way how to choose the gamma. The larger you choose it, the more protection you have against worst case scenarios. How about causality? It's impossible. But if you choose gamma infinity, it corresponds to invariance of residuals with respect to arbitrarily strong shift perturbations which are generated by A. It's not any perturbation, but it's shift perturbations which are generated by A. And the true causal concept would mean, well, it is something different. It's invariance with respect to all perturbations not directly acting on Y. So these are different concepts. But somehow we think this is a connection, and this is interesting. The notions are related. Partially we can quantify this, and it means even in ill-posed situations, if we choose gamma very large, gamma infinity, we can interpret these coefficients. These are not the causal coefficients, but they're somehow, Ed called it the watered-down causal coefficients, right? It's some sort of a version which says, okay, if I choose these, if I interpret these coefficients, it kind of means that they are stable under arbitrarily strong shift perturbations. And I think in many examples in science or in biomedical examples, you typically don't fulfill the assumptions for causality, but maybe you're more likely to fulfill these assumptions and you still have a more meaningful and more causally oriented interpretation than simply running regression. Okay, so this is a data set on prediction only. This is about bike rentals. So we have hourly counts of bike rentals in Washington, D.C. Sample size is a bit more than 17,000. The goal is to predict bike rentals based on 4 covariates. A very low dimensional problem, a huge sample size. And the covariates are meteorological: temperature, feeling temperature, humidity, wind speed. What is the anchor? The anchor is time. We use time as an anchor. We choose blocks of consecutive time points. This is my anchor, and the unit of an anchor is a day. So every day is a discrete value of the anchor. Of course, you have to adjust for the usual thing, for hour, working day, weekday, holiday, and so on and so forth. Now, what we want to evaluate is not the squared error risk. I want to evaluate the worst case risk. Over what? Well, okay, I'm not sure. But that's actually hard. How do you evaluate worst case risk in a data set? If you do cross-validation, what is the worst case? You don't know. And this is a bit a hack around it. So under some assumptions, and I must admit that, under some assumptions, the worst case risk is actually a quantile of a conditional of the expected squared error conditioned on A. So this can be made rigorous. So if I look at the worst case risk for a large gamma, this is an alpha gamma quantile, and the quantile must be large. Okay? And so in my data set, what I do, I just consider high dimensional quantiles of the squared error and see how well that works. And my time is going over. The point is, okay, we get about 15 to 25% gain over just standard least squares. I'm not saying this is a great result per se. This is just more a way of thinking how you can just improve over standard least squares. We also run experiments with random forests. You can do something like that too. You can do ordinary random forests, and if you're in a heterogeneous environment, we empirically see that sometimes you can improve over ordinary random forests by using this causal regularization. Okay, I think I should skip that in view of time and conclude. At least to me, there are surprising connections, or perhaps surprising connections between causality and invariance and robustness, and some of them were known. I brought up Havelmo a long time ago, and some of them are maybe more novel, and I think some of them are especially interesting also in the advent of large-scale data where we see a lot of heterogeneity. And we can think a bit of a folklore type version of what I told you in my talk. The practical implications are somehow, if you regularize towards causality, you can do this in one way which I explained to you, maybe there are other ways, but if you regularize towards causality, then you get predictive stability. Now the next one is a bit more dangerous to say, but I say it now. If you see predictive stability, suppose there's a scientist in the lab, and you have a lot of perturbation experiments, and you kind of see predictive stability. If you're conditioned on some variables, there's more or less the same thing which is happening. It's not the causal thing, because maybe the assumptions are not met, but it's kind of the watered down causal effect. It's a more causally oriented interpretation than simply ignoring this thing. Okay, so my story is, it sounds like heterogeneity, non-stationarity is bad, right? It's a nuisance. I'm telling you it's actually good. You can exploit it. Thank you.
Thank you, Tina, for a wonderful talk. Any questions?
Yeah.
You talked earlier about the situation where you had a number of interventional environments and also an observational environment. Now, if you're looking for invariances there, you could have the following problem, that because the observational environment might be subjected to confounding in various ways which aren't present in the interventional ones, the kind of causal relationships you want to find in purely interventional environments won't be present in the observational environment. And if you insist on finding something which is common to all those environments, isn't that going to distort your findings?
No. So you're saying that somehow the idea that this A in my language, that this points just to the H, is kind of maybe over all the different environments is maybe not such a good model.
Well, I'd be worried about, if you've got a lot of interventional environments, why not just discard the observational one as possibly getting in the way?
Yeah, it's a good point. I don't know. So, but it somehow has to do, suppose in my gene example, if I really want to solve this more precisely, what I would like to have is, of course, enough data, or at least some replicates about the same intervention or a similar intervention, and then I could try to understand actually the mechanism of how that would change in comparison to the observational regime, right? I need to somehow, if I try to model that, this would be very valuable, but I need somehow a bit more data, and this is maybe possible in certain applications. So if I just have one perturbation, like in my gene knockout example, it's just very hard to go further. But if I have that information, I could actually try to see whether there is change or not, right? Or whether this assumption makes sense. But okay. It's a lot of open issues here, I think. So I want to make clear here, this is not the solution to the causality problem, of course. And this is kind of this new word, the watered down causality. I don't know what do you think about it. But my point is, we should do something which is just more than standard homogeneity regression. It just gives us much more meaningful results. in terms of predictive robustness, I believe also in terms of interpretation. It's not the causal thing often, unless we make strong assumptions, but it's towards something better.
This may be an irrelevant question, but it occurred to me. Is there somewhere in this a relationship? Sorry, I'm having trouble. I'll leave it. Maybe we'll ask you after.
We can have it at the wine partly.
So, do you have any sense how this scales in the interventions? Because say your biologists come to you and they say we've done 100 knockout experiments, we could do a few more. Should we do another 100 or 200, or which ones? Is there any way to connect this?
Well, I think the answer is I don't know how to do that, but it's in a way the same problem like if you plan clinical trials, right? You make an assumption on the noise, right? So of course I could try to do a pre-analysis with this and then see, we can see so many.
You know something about the distribution of all the genes together without your outcome. And you,
Yeah,
if you know that two genes are very similar, you wouldn't knock out both of them. So it's kind of like getting
Yeah,
into the
that's
design
that.
question. That
That could be done, but I think that would also be interesting to go the other direction, right? You want to, okay, you knocked out a gene, it's very similar to this one. So what they do, and I mean some people here are experts in the room, but I think they look at pathways, right, and say, okay, you knock out one gene there, and I want to see another pathway, and so on. But I don't see at the moment how I can do some sort of a statistical argument how to do that.
Sorry?
You remembered.
Well, it's sort of come together now, and I think the basic point I wanted to put is the distinction between what you might call a necessary and a sufficient condition to be causal. For instance, if I want to win the lottery, I have to buy a lottery ticket. But was that causal?
No, it's not. I don't know.
It's certainly not.
I don't know. Maybe I think it's a good occasion to speak at a wine reception on more philosophical topics. But of course, it is a relevant thing how people act and behave, right?
Any other questions for Peter? I'll remind you that there is wine outside.
Right, so I have one question. So, this notion of perturbations, you talked about the shift perturbations. But conceptually, it seems that you could ask the same question for other sorts of perturbations.
I think so. Yeah.
I mean, is there a?
So this is kind of the beauty of the math, right? So the shift perturbations at the moment, they just fit very nicely into this result here. So with shift perturbations, you can get this exact duality, which I think is kind of nice and neat. Of course, it has to do with the anchor structure also, which is this kind of additive exogenous term, right? And so you replace the exogenous term through a shift perturbation. If it could be, it has to be almost additive, I think, at least with the proof techniques we used to come up with this result. Because the observed heterogeneity comes additive, m times a, and so we want the perturbation also of that form. Maybe I should point that picture, so I dropped it. But what we do actually is, in a way, this is robust optimization, they do something different. But we want to be robust over a class of things. And what we actually do, we learn from heterogeneous data how the class looks like, right? And so the idea is the shifts are kind of versions of this MA. And then we protect against shifts just by amplification of that. This is in a way what we do. And it's becoming quite more complicated. If you move away, if some sort of the anchor has a different structure than your perturbation, I don't know how to do that. But that's somehow the reason.
So
So in economics, the big problem is instrumental variable regression is weak instruments. So what about anchor regression? I don't see how you would check for weak anchor.
Yeah, but it's the same issue. So what I didn't say, but what I can say, of course, if the anchor is an instrument, we get the same results. Like if I take gamma infinity, I get a two-stage IV estimator. If I have only a weak anchor, a weak connection, then in that picture, it's just sort of I don't learn almost anything. And the stronger the anchor, or the more anchors I have, the more heterogeneity, the higher dimension of the instrument, the better it is to identify interesting perturbations. And if it would be an IV model, and if I have enough instrument, I would identify the causal effect. But it's the same story. So strong anchors are better than weak anchors.
But do you know which anchors are weak or strong?
No, I have no idea. I just use time, or I would use geographical position if I have a large data set. No, I don't know. I have no idea.
Okay, if there are no more questions, let's thank Peter for a wonderful